Now let's stick to 2D. Let's consider a case with two features, or we can call them predictors as well in statistics language, psi1 and psi2. Right? So our design matrix in this case is what? Well, it's the vector of our feature, the matrix of our feature vectors. What's the feature vector? Psi1 and of x as a random variable, x, and psi2 of x. Right? That's our feature vector, this column vector. Right? So evaluated at x1 with the realization x1, that's the first row of our design matrix, down to the realization xn. So our design matrix looks like this, and the columns, I'm going to call this column here phi1, and I'm going to call this column here phi2. Right? And so we can write 1 over n, this matrix, this symmetric positive definite matrix, like this. So this should be obvious, right? So if we transpose this, these become rows, right? And then when we multiply that by phi, we're going to get essentially the dot products of these column vectors. Right? So the first one dot itself, this one will be the first entry, and this one along the diagonal will be this dot product with itself, and these off diagonal entries will be this dot this, and they're both the same. So these are the same. So this is symmetric, and it's positive definite matrix. Okay, now what? So each entry is a sample second moment, but we haven't centered it yet. We're not assuming yet that these feature vectors have zero mean. So this feature vector that we've defined. So let's sample things. So I'll show you how we can justify this. We can standardize the features in the following way. So we do this this part here by dividing by the sample standard deviation. So if we have, let's say, psi1 of xi, right? The sample mean is defined as before. It's 1 over n, sum from I equals 1 up to n, of psi1 at xi. Then the sample standard deviation is 1 over n, sum of psi I minus at xi minus the mean psi bar. So, oh, that's not I. So let's do this for 1, the first feature. 1 psi 1 bar, and the whole thing is squared from I equals 1 up to n. So this, we can call this the sample variance, right? And so let's call this S squared. Then the sample standard deviation is going to be the square root of this. Square root of that, which is S. So what we do after we've centered is divide by S, right? And the new transformed variable will satisfy this condition. So all in all, what we're saying is this: we start out with the psi i's, psi1 xi's, the values, and we rescale them and center them in the following way. We define psi 1 tilde at xi to be equal to psi 1 at xi minus the mean, psi 1 mean, divided by s, the standard deviation, given by this thing here, the square root of this sum. And if we do that, then we'll satisfy this condition for psi1, and we'll satisfy this condition for psi1. And we do that for both psi1 and psi2. So for psi2, we do exactly the same thing, whereas now we're going to have the standard deviation. So that will be based on the psi2 values here, the mean psi2. So doing this performing this transformation, this standardization, will lead to this. Okay, so this will then mean what? Well, this will mean that from this condition here, these dot products are both equal to 1. Right? We scaled to unit variance both of the features, psi1 and psi2. Now the columns are centered, and so this sum here is going to be our sample covariance because we've got zero mean now over it. We can assume zero mean now that we've centered it, centered the data. So, so we can set this quantity here, which is this here, as the sample correlation. Let me call it rho. And so our matrix becomes what? Well, along the diagonals, since we've scaled the variances, we've got variance of sample variance of psi1 is 1, sample variance of psi2 is 1, and the correlation or covariance between psi1 and psi2 sample is rho. And obviously, it's a symmetric matrix. Covariance between psi1 and psi2 is the same as the covariance between psi2 and psi1. Okay, now let's study the eigenvalues of this matrix here. So the eigenvalues of this sample covariance matrix. Well, the characteristic polynomial, right, in order to find the eigenvalues will be what? So we form, so what are the eigenvalues and eigenvectors satisfy? Well, let's call this A, and they will satisfy A, V, so the eigenvectors will be V equals lambda V, or A minus lambda I, V equals 0. So the characteristic polynomial is formed from this matrix. So this matrix here is this matrix, so it's going to be 1 rho, rho, and 1 minus lambda times I, which is going to be lambda, 0, and 0. So we're going to get this matrix 1 minus lambda. We'll get rho here, and 1 minus lambda here. Right? The characteristic polynomial is this times this minus this times this, the determinant of this. So it's going to be 1 minus lambda all squared minus rho squared. And that has to be equal to 0. And that's the condition that will be satisfied for the eigenvalues. And so we get eigenvalues of 1 plus or minus rho. There are two eigenvalues, lambda 1 we can write is 1 plus rho, and lambda 2 we could write is 1 minus rho. Okay, what does this tell us? Well, let's have a look at what happens for different values of rho as the correlation increases or decreases. So if rho equals 0, in other words, our features or predictors are orthogonal, meaning they're uncorrelated, they will be orthogonal, right? And we will get these ellipses where the axes are aligned along the axes x1, x2, or theta1 and theta2 in our case. Now, what if rho equals 1? Well, if rho equals 1, that's the definition of perfect collinearity or exact collinearity. In other words, we will have this kind of relationship. Psi1 is a linear transformation or affine transformation, to be more precise, of psi2, or vice versa. So psi1, the random variable psi1 of x, will be some constant plus another constant times psi2 of x. Right? They're perfectly correlated. And we can have a situation in which they're nearly correlated or near collinearity, which is as rho converges towards 1, tends towards 1. So as rho gets closer to 1, as our correlation between psi1 and psi2 approaches 1, we'll have two eigenvalues. Right? We'll have lambda 1 equals 1 minus rho, and lambda 2 equals 1 plus rho, right? And as rho tends to 1, this is going to tend to 2, so we can call this lambda max, right? This lambda 2. So it's not 2, but it's approaching 2. It's getting closer to 2 as rho approaches 1. This one is approaching 0. We can call this lambda min, the minimum, the smallest eigenvalue and the largest eigenvalue. There are only 2 here. So what effect will this have? So this corresponds to near collinearity. The extreme case is exact collinearity when rho equals 1. Right? So in which case we have one exactly 0 eigenvector. So collinearity means basically that one of the eigenvectors becomes very small. It starts to approach 0 or it approaches 0. Now in the eigenbasis coordinates, which I showed you before, level sets of the empirical risk take this form. Right? So these are transformed coordinates, theta 1 and theta 2. They're transformed to u1, u2. So remember, in that case, what we did was using the eigenbasis of phi transpose phi, we transformed phi into u, which was defined as q transpose. These are the columns of the eigenvectors of phi transpose phi. Right? Our matrix that I wrote down earlier, and we've just been studying again its eigenvalue properties times theta minus theta hat, right? Where this is the empirical risk minimization solution. So this is what the level sets look like, right? They go from looking like this, theta minus theta hat, phi transpose phi, theta minus theta hat, that's transposed, to looking like this, u transpose what was it? Q lambda, sorry, lambda, where this is a diagonal matrix with lambda 1 and lambda 2, right? So in this case, we're going to have the lambda max and lambda min times u, right? And this contour here or level set is equivalent to this contour or level set, right? So it looks like this. It's an ellipse with minor and major axes aligned along the axes of u1, u2 axes. And the axes lengths are what? Well, for a given constant c, the axes, let me make sure I'm using the right. Oh, yeah. Yeah. So the semi-axis lengths we saw take this form. So they are the value of the constant c where we're defining the level set divided by the respective eigenvalues. So you can see what's going to happen here. As one of these, let's say lambda 2, tends towards 0, so this would be our lambda min. Why do I keep writing A2? It should be B. B is going to tend to infinity. So what does collinearity look like geometrically? Well, this is saying that, so if in our transformed coordinates, we draw our ellipse, right, like this, if this is B, this length, and this is A, as B tends to infinity, this is going to become a very long, thin ellipse. Oops. Let me try and capture a bit of that horizontal axis there. It's going to tend towards basically almost a straight line. Right? Or it could be going this way. But either way, it's tending to some kind of long, thin ellipse, either oriented vertically or horizontal. So that's what collinearity would look like. If we look at it geometrically, this is how it appears. Okay, and this suggests that we're going to get some kind of instability. Well, we can already see this. Right? So what are the consequences? Let's spell them out. precisely, let's use a bit of technical language. Well, we can look at the condition number of this matrix, which is defined, and we call it kappa, as the maximum eigenvalue divided by the minimum eigenvalue, which is this, and that tends to infinity as rho tends to 1. Correlation tends to 1, perfectly correlated. Right? So what is this telling us? It's telling us that collinearity leads to a large condition number, and this matrix becomes ill-conditioned, which means it's difficult to find its inverse. Right? It's going to be very difficult. We'll have to start using all kinds of tricks like pivoting to try to find its inverse, and that might not necessarily help anyway in the end, even full pivoting. So let's see exactly why. Well, first of all, for a unitary matrix, I told you this before, its inverse is equal to its transpose. And in our eigen decomposition, so when we decompose phi transpose phi, the eigen decomposition, we wrote it like this: Q lambda Q transpose, right? So this Q here, the columns of this are going to be the two eigenvectors corresponding to lambda 1 and lambda 2. Right? This is just a 2 by 2 matrix in this example we're looking at. So this is a 2 by 2 matrix. The columns are eigenvectors which are in R2. And the inverse of this Q is equal to its transpose. So we could equally, well, write this like this because they are actually the same thing. All right. So from that eigen decomposition, we can write this. So what's the inverse of this, which is what appears in the Moore-Penrose pseudo-inverse? It's going to be Q lambda Q transpose to the minus 1. Right? So that is equal to this to the minus 1, because that's equal to that. So now Q transpose is Q minus 1. Right? So we can do, what's the inverse of this? Is going to be Q minus 1 times lambda minus 1. So again, like we do with transposes, we swap them around. So we start with this one, take the inverse of that, times the inverse of that, times the inverse of that. Lambda minus times Q minus 1. Now the inverse of the inverse is just going to be Q. And this is lambda to the minus 1. And the inverse is equal to the transpose. So this is Q transpose. So we end up with this. Right? Now what's this? If we have a diagonal matrix like this, which is what this is what lambda is. Right? The inverse of a diagonal matrix is just 1 over this, and we still get zeros here. Right? So the inverse of a diagonal matrix is very easy to find. We just take, it's just the reciprocals of the diagonal. So that's what this means here. Diag of 1 over lambda 1, 1 over lambda 2, which is this matrix here. So this is the inverse of this, which, if you recall, appears in the Moore-Penrose pseudo-inverse. So what is our ordinary least squares or empirical risk maximization with a square law solution? It's this thing here, which we can write as follows. So what is this? Well, we can write this equivalently as, so when I decompose Q lambda Q transpose, so this is phi transpose phi is equal to this. Another way of writing this is as the sum of outer products as I defined them before. Lambda I V I V I transpose. Right? So if we put a minus 1 here, that's 1 over lambda I times this outer product here. Right? So this is another way. So these are the eigenvectors which form the columns of this. So you can work this out yourself. It's fairly straightforward, this relationship. It's just messy, but it's straightforward. So again, these are the eigenvectors of our matrix, phi transpose phi. So we get this relationship here because what I've done is I've replaced this right, which we've seen is equal to this, and that can be written like this in here, times phi transpose phi. Now, if one of these eigenvalues is small, 1 over lambda I is obviously going to become very large. And this is going to lead to instability. So if we work with a fixed design, that means we don't consider the xi's as realizations of random variables. We control them. So later on, I will discuss this in more detail, what a fixed design actually is. And that's actually the usual scenario in most regression. We actually consider these design points, as they're called. This is terminology that comes from design of experiment, to be fixed. So small perturbations in our data, well, what's our data? Now it's just y, because these are just fixed. They're going to get amplified. So this thing is going to blow up. This solution is going to blow up, basically. If one of these lambdas becomes very small, its reciprocal becomes very large. This solution will blow up. It will give us all sorts of spurious results. Even with a small change of this y, we'll get a massive change in this whole result, a massive change in our theta hat. And this is a form of instability. And it's caused by this collinearity, which is what causes one of those eigenvectors to become very small.